Okay, so did I share my screen yet? I did not. Let me do that. So before we can go to the spectral theorem, there's like a small little like lemma which is useful for it. But this one says that if you have an orthogonally diagonalizable matrix, and what does that mean if we can orthogonally diagonalize something?
So for an orthogonally diagonalizable matrix, that would be a matrix where you'd be able to get values along the diagonals, and it would be able to be simplified so that then like you would have now that none of them would be based solely off of other ones. Is that right? Where like they're all linearly dependent vectors?
Kind of, but like it's a bit stronger than a statement about just diagonalizability. So with diagonalizability, what this is saying is that A is similar to a diagonal matrix, right?
Mm-hmm.
When we're saying it's orthogonally diagonalizable, how is it different from just being diagonalizable?
I don't remember.
So now we're saying that this matrix P and P inverse also has to be
Orthogonal.
Yeah.
Okay, right. Yes, okay.
So diagonalizability is kind of saying, oh, it's like a diagonal transformation with respect to this basis. Now we're saying you can think of it as like a scaling with respect to not just any basis, but an orthonormal basis. So what this theorem says is that this condition, this happens exactly when our matrix is symmetric. Right? So it's not just that if you have a symmetric matrix, you're going to be able to find this orthogonal basis, but any matrix where you can find this orthogonal basis has to be symmetric. So the spectral theorem is saying more. It's saying now if we have this symmetric matrix, we can find out a lot about it. So from the above lemma, we know it's going to be orthogonally diagonalizable. And does anyone remember the other condition, the other consequences, which I guess are also kind of coming from this orthogonally diagonalizable part?
Is it that A equals A transpose?
Well, so that's the hypothesis. If we have A equals A transpose, we're saying it's a symmetric matrix, right?
Oh, yeah.
So the hypothesis is if A is a symmetric matrix, if A equals A transpose, then we know a couple of things. So this is the first statement. Does anyone remember what else we can say?
Could we say n distinct eigenvectors?
Yeah, or distinct eigenvalues, right?
Yeah.
We have different eigenspaces. So it's well, actually, it's not quite distinct eigen values, but they're you're gonna have n eigenvalues, and that's counting multiplicity. So you can have one value be like a multiple, counted multiple times, right? For example, like the identity matrix is symmetric, of course, but we have the eigenvalue 1 comes up twice. So if we have, if it's going to be diagonalizable, what else is true about these eigenvalues?
They have to be distinct.
Or not quite. Remember that if we have, we can diagonalize matrices with non-distinct eigenvalues, right? Like I said, the identity matrix works, but so one of the facts that we have is that n distinct eigenvalues always means it's diagonalizable, but diagonalizable does not always mean that we have n distinct eigenvalues. But you can say something about the eigenvalues. And remember what that statement is. And it has to do with algebraic multiplicity versus geometric multiplicity.
Is it
Do
that
they have to be the same?
Yeah. So if it's diagonalizable, that means that the dimension of your eigenspace, which is the geometric multiplicity, is actually equal to the algebraic multiplicity. So in this case, because it's diagonalizable, whichever n eigenvalues we have, if it shows up, twice, for example, here, that means that the eigenspace actually has dimension 2. And with non-symmetric matrices, right, we had examples, like I think this is one of them, where your eigenvalue shows up twice, but now your eigenspace is one-dimensional. So for symmetric matrices, this will never happen. You'll always have the case where you actually have your eigenspaces equal to the dimension of your eigenspaces equal to the algebraic multiplicity. Let me just actually say geometric multiplicity equal to algebraic multiplicity for each eigenvalue. So that covers the diagonalizability part. What does this orthogonally diagonalizable part tell us about these eigenvectors?
the vector in one eigenspace has to be perpendicular to a vector in another eigenspace?
Exactly, yeah. So vectors from different eigenspaces are orthogonal. Remember in the non-symmetric case, we have eigenvectors from different eigenspaces that are literally independent, but orthogonality, yeah, is a much stronger condition than linear independence, right? So what we're getting is like now before we could have, say, some eigenspace that might be looking like some plane, and this other say eigenspace that's like another like line kind of like cutting across the plane, maybe not perpendicular. So then you have like this eigenvector here, and you have some eigenvectors in your plane, and this eigenvector on this line isn't necessarily perpendicular with the ones on this plane. It's literally independent, sure, but there's no reason it has to be perpendicular. With this symmetric, oops, where did this go? I think Evernote just crashed on me. So let me close that and reopen it real quick. Oh. I can switch to the whiteboard, I guess. Let's see. How do I start a whiteboard on Zoom? Does anyone know how to actually pull up the whiteboard?
I think you click on share screen and then there's a whiteboard option.
Okay, I see. Cool. Thanks. Cool.
No problem.
Full screen. Yeah, so if we have a symmetric matrix, we're saying that the eigenspaces are never going to look like that. It's always going to have a perpendicular. The other eigenspace will always be perpendicular to this one, right? Any questions about that theorem?
What is the name of that theorem again?
This is the spectral theorem.
Spectral theorem. Perfect.
Yeah.
Thanks.
I think it's 7.3. Yeah. Or theorem 3 in section 7.4.
Thank you.
Okay. I went over a couple of problems on Friday's section, but not too many people were there. So would you guys want to try other problems about this? Or would you want me to talk about 7.4? Oh, this is 7.1.
Maybe a little both.
Okay. Let me take a look and see which of these problems were easier and not too long. Yeah, let's try actually finding this orthogonal diagonalization for a matrix. Did anyone have any specific problems from the homework that they wanted to go over? Or should I just assign one at random?
Yeah, I had one, or I don't know
Okay.
how to do 13 for 7.4.
Oh, okay. Any from 7.1 first? Okay, I'll give you guys one of the smaller ones then. I think 13 wasn't assigned. So,
Oh, it wasn't?
oh no, for 7.1.
Oh, okay.
Yeah. So I'll take a look at the problem in 7.4 while you guys work on this and see which one that was. Or orthogonally diagonalize this matrix here, 3, 1, 1, 3. Yeah. Okay, 13 is just finding an SVD for 7.4, right?
Yeah.
Okay, yeah, we can go over how to do that right after this. Oh, I was muted. I was talking. My bad. Yeah, so can you guys see the Evernote screen again?
Yeah.
Okay, so what's the
Yeah.
first step to diagonalize this?
Should find the eigenvalues.
Yeah, and what did you guys get for those?
Negative
2 and 4.
So,
Yeah, I think the characteristic polynomial is
oh
what?
yeah.
3 minus lambda squared minus 2, right? Or minus 1, I think.
-1.
Yeah, and then if you expand it, it'll have these roots. So then we have the eigenvalues. What do we do to get the P, the diagonal matrix? Or first we need this P to be orthogonal, right? So what's the difference between just diagonalizing and orthogonally diagonalizing? Yeah, go ahead.
Is it that when you orthogonally diagonalize, you want to find the? I know you normalize somewhere, or you normalize the eigenvector you find.
Right. So with P, we're going to normally we find some eigenbasis, right? And now we're going to find an orthonormal eigenbasis instead.
Yeah.
So let's start by finding the eigenvectors. How do we find the ones corresponding to lambda equals 2?
You subtract 2 across the diagonal.
Yeah. So then we get 1, 1, 1, 1. And what do we do with this matrix?
That equal to 0.
Right. So we're trying to find this times x is equal to 0.
Oh yeah.
Yeah. Did you guys figure that one out?
Yeah, it should be -1, 1.
Right. And then, oops, for lambda equals 4, what do we do for that?
Same thing.
And the eigen vector is,
1, 1.
yeah. So are these two vectors orthogonal?
No.
Why not?
Actually,
They should
wait.
be-
Yes, that'd be when you multiply, that'd be 0.
Yeah, so you can verify this with direct computation and check that this is -1 times 1 plus 1 times 1 is 0. But also because they come from two different eigenspaces, we know that they're orthogonal, right? By the spectral theorem. So what would we do if we only had one eigenspace? Like, let's say we had just lambda equals 2, and like some other eigenvector we had looked like, I don't know, like maybe -1, 2, for example. What would we do then to get orthogonal eigenvectors?
You'd use Gram-Schmidt's
Yeah,
rule.
so then we use Gram-Schmidt. In this case, it's a small 2x2 matrix with all the eigenvalues just having multiplicity 1. So we don't have to use that in this case. But in general, if you see a problem about orthogonally diagonalizing, you might need to use Gram-Schmidt to get orthogonal eigenvectors in the same eigenspace. Does that make sense?
Yes.
So then all we need to do is normalize these vectors. And how do we do that?
You
Take
divide.
the magnitude.
Yeah, so we're going to divide it by its magnitude. And what's the magnitude of each of these guys?
Red 2.
Right, so we get 1 over root 2, 1 negative 1, 1 over root 2, 1, 1. And this is our orthonormal basis. And then to actually get the orthogonal diagonalization, you just plug in. So you get 1 over root 2, negative 1 over root 2, 1 over root 2. Times, and then this one on the left corresponds to 2, right? So you get that, and then just the inverse of the matrix on the left. Makes sense? Questions? There are a few other conceptual things. I think I just went over them in Friday's section, and I'll post that video if you want to like see the true false from the section as well. Let me briefly talk more about one of the concepts at the end of this chapter before moving to 7.4. So one of the things we can do is when we have an orthogonally diagonalizable matrix, right? We can take this decomposition of it, where we're going to take U is an eigenvector, right, of A for some we have a bunch of U's rather, not just one U, orthonormal basis. So we're saying is that when A is symmetric, we have this orthonormal basis of eigenvectors always. So now, given this basis, we can actually write A in a really nice form. We can take each eigenvalue and then take this matrix that we get by multiplying each eigenvector with its transpose and write it as a sum of all of these. Essentially, what's going on here is that each of these UU transposes is kind of projecting some vector onto that subspace spanned by U, right? So really what you're kind of doing is now you're writing like this transformation AX, you're taking X and then writing it as a linear combination of these different basis vectors. And the weights are given by these eigenvalues, right? So in essence, we're kind of breaking up this A into like each of these pieces kind of corresponding to the eigenvectors. Does that make sense?
Yeah.
So this decomposition only works for symmetric matrices because we have to have this orthonormal basis. And now the goal is, can we extend this to any matrix? And that's what we're going to be trying to do with SVD. Flip over to 7.4 so we don't misstate any of the theorems. So what's going to happen is we're going to use one really important fact. And that's that for any matrix, A transpose A is going to be symmetric. Right? So we can kind of do this process with A transpose A. And now what we're going to do is kind of have this weaker condition than being orthogonally diagonalizable, but still kind of very powerful expression. We're going to take A, and then we're still going to write it as a diagonal matrix times something, but now we're going to generalize this to any matrix, not just n by n. So instead of having these be square invertible matrices, we can take we can take these to just be orthonormal in kind of like this is m by n, right? Then we can have the one on the right be n by n and the one on the left be m by n. So it's not going to be a matrix and its inverse. These are now two different matrices, but they're still matrices that are going to be orthonormal or orthogonal matrices. And yeah, questions about that part so far? So intuitively, we can kind of think of this as any linear transformation. We're going to kind of find these two corresponding bases that you're kind of just like stretching one basis to be another. And since these are orthonormal, you can think of this as these as being rotations. So we're taking some linear transformation and then writing it as some rotation and then some scaling. And this is not necessarily just a scaling, right? Because you might be going into higher or lower dimensions. So you might also be losing some information or trying to add extra dimensions that you can go in. And then rotating again to some other basis. So you're kind of trying to capture this one linear transformation with a bunch of smaller, kind of more manageable steps. And the nice thing is that, do we do this already here or later in the chapter? We can kind of do the same thing once we have this, where we're going to write it as the sum of, now instead of eigenvalues, you're going to have singular values. But let's go into actually finding this decomposition, since it's a little bit tricky. So the first step is we're going to need to find A transpose A, and then find its singular values, or the singular values of A, rather. So the singular values are what we call the entries of this diagonal here. And they're going to be defined as the eigen values of A transpose. Or A transpose A, I think, misspoke. Then our V matrix is going to be corresponding eigenvectors. And lastly, our U matrix is going to be the images of those eigenvectors under A. Cool. Questions about this process? So let's actually go through it with one of these examples. So find the SVD of 3, 2, 2, 2, 3, minus 2, right? Yeah. So what's the first step going to be? You guys probably have time to finish the whole thing, but let's go through at least all the parts together if we can. So we're going to need to orthogonally diagonalize something, and what's that going to be?
Is that just A? No.
Well, A isn't symmetric, right? It's not even square. So we need to
Yeah.
get a symmetric matrix we can orthogonally diagonalize.
Right.
And what's that matrix going to be? Anyone have thoughts?
Oh, is it AA transpose?
I think it's A transpose A. I might have mixed them up. It should be A transpose A, right? Yeah. And did anyone find what that matrix looks like yet?
Not.
And then since A is 2 by 3 and A transpose is 3 by 2, this will be 3 by 3, right?
Yes. Okay, so I think the matrix would be 12, 13, -2 along the first row.
12, 13, -2,
And then 13, 12, -2.
13, 12, -2,
And -2 to -8.
-2 to -8. Oh man, this is a big matrix. I think it's true that the eigenvalues of this are the same as the eigenvalues of A transpose. I'm not sure if that's true. I want to say it's true because it'd be easier to compute.
So when do we
Um,
know if A transpose A or A transpose?
So the book says A transpose A, but I think you can use A transpose for the eigenvalues, because this one's kind of a long computation.
Oh, okay.
Let me
But
say that
But
again.
wouldn't it be 3 eigenvalues here, but then only 2 eigenvalues for the other one?
Yeah, you're right. You only consider, I think, the first R eigenvalues for singular value decomposition, where R is the rank. So if you have like the extra ones, you won't consider them. Well, let's find the eigenvalues for this first, and then go on from there.
Oh gosh.
Or are we going to do that? Let's do. Okay, I think the eigenvalues are going to be the same, and the extra ones will be 0. So I'm pretty sure we can use A transpose to find the eigenvalues, but then we're actually finding the vectors for V and U. You have to keep the dimension consistent, make sure you're putting the right one on the right side. So I think this computation is easier, and you get what looks like 17, 17, 8, 8. And the characteristic polynomial, this is much nicer. Or like, it's still not nice, but it's relatively, it works out much more nicely. I'll just give it to you guys since we don't have too much time, but it's lambda squared minus 34 lambda plus 225. And then that gives you that the eigenvalues are 9 and 25. I think I made a mistake here. The singular values aren't exactly the eigenvalues. They're going to be the square roots of the eigenvalues. Essentially just because like we're multiplying by A and A transpose, so it's kind of going to be like twice as big as the actual thing we want to get. So we need to take the square root to actually get these values on the diagonal. So then anyone know how we might get U and V? Once we have these. So what we're going to get is I think how it works out is that if you use A transpose A, then the corresponding vectors will be in V, because they'll be like if we did the 3x3 one, then we'll put the corresponding vectors in the 3x3 matrix, right? But now if we're finding the 2x2 vectors, we have to put them in the 2x2 matrix, the eigenvectors. Yeah, I think this example is kind of rough if you don't realize this trick of using AA transpose instead. But I also don't think they do that earlier in this chapter. So basically, once you find the eigenvectors, those are going to go in, we're trying to write this as Q sigma B transpose, right? These guys are going to go into B transpose here. And then this guy will be the sigmas we found, right? This guy is 2 by 3 because that's what A started off as. So that matrix will look, I think it's 5, 3, and zeros. And then U is, so A goes from R3 to R2. We want to go from R2 to R3. So we need to multiply these vectors by A transpose to get U. Yeah, I guess it doesn't really like make much sense if they have time to explain the difference between trying to do it this way and then the longer way. But this is one strategy, and we can compute the actual numbers and go over that next time if that works, because I don't think we have enough time to go through it now. Does anyone have questions about like the general approach of SVD?
Not on my end.
Nope.
Okay. Yeah, I think in general, you can usually stick to the method they outlined in the book. I think where do they actually outline what the process is? I don't think they have like a theorem for it, but I think on page 420 is where they give the process, and that generally works. I think for this problem, it's actually really rough to try and do it that way. This other way I think is a little bit cleaner, but I'll explain like the details next time.
Okay, thank you very much.
Yeah, totally.
Thanks.
Yeah.